very much for coming. Thank you very much, Sandro, for putting us in contact with Samo. So Rosat is a researcher at the Operations Research Center as a group in decision analysis from Montreal, Canada. Right? And he holds a PhD in applied mathematics from Polytechnique, Montreal, and a Master of Engineering in École Polytechnique, Paris. And he's going to be talking today about fostering integral decisions in the simplex algorithm, application to scaling. Thank you very much, Sam.
Thank you very much, Rodrigo. So, hi everybody. Thank you for inviting me. Thank you for Rodrigo for making it possible, technically and everything, and Alessandro making me in contact, putting me in contact with people here. I sent an abstract a few months ago. I sent a title, and the title is slightly different from that on the abstract. I will be talking on one side of the project more than on the other side. It's a little bit different of what you had in the text. But if you have any question about what was in the text originally, of course, I'll be happy to answer it and to discuss it with you afterwards. So this is joint work with other researchers from Montreal. Brice, Ismaël, Andrea, Frédéric, and François. Others worked on the projects too. And yes, he's been taking a position in Polytechnique for a few months, and he's full-time, I mean, most time now in Montreal, from September, I think. I worked with him in Bologna when he was there, and then he moved to Montreal. Maybe I convinced him. Don't think so. I wouldn't be too sure of this. Yeah, so he's working now in Polytechnique. So I'll be talking about how to foster integral directions in the simplex algorithm and how to go toward what could be an integral simplex. So simplex, are you all familiar with linear programming, integer programming? Okay. So the idea is to mimic the simplex algorithm, but instead of going from one linear point or real numbers to one other, the idea is to be on an integer point and to go to the next integer point. So that's what we will see, but I'll explain the whole thing throughout. So I'll first present what an idea of integral simplex could be, and then how to make sure that every step you take leads to another integer solutions with different techniques. Ensuring it is complicated, making it as sure as possible so as it is. That's what we do. So I'll start with the application side to show a bit what we are doing. We're doing scheduling, set of tasks, and a set of possible schedules. And usually that's how scheduling is modeled often, especially big problems. And we want to select schedules so that they cover all tasks and exactly once. So on a graph, typically the tasks to be performed A to H, and possibilities could be schedule 1, schedule 2, schedule 3. And with all these, I cover each task exactly once, and at least once and not more than once, because I don't need more people to perform them. So in a mathematical point of view, the first column of the matrix corresponds to the first schedule doing tasks B, E, and H. Each task is a line, is a row of the matrix, and each possible schedule is a column. So basically the matrix is 0, 1. 1 when the schedule performs the tasks, 0 otherwise. And what I need is to find a set of columns of the matrix so that on each row I have 1, 1 exactly. And this is called the set partitioning problem. So it corresponds to partitioning set A to H into different sets. In our case, sets are schedules. And so typically another possibility could be this one, A, B, D, and H. And then we would have another column in the matrix. So for those who are more familiar with this, typically that kind of problems are solved with column generation. So you start with a subset of the schedules, and given the solution that you find, you try to add new ones such that it's better. We'll concentrate on the static version of the problem, and we'll see column generation in the future work that we can do. So basically the idea is to solve this problem called set partitioning. Each schedule has a cost. I mean, the objective is to minimize the sum of the costs, given that we want a feasible schedule. So the formulation is this one. Linear programming is the red constraints. So we have linear constraints. Matrix A is 0, 1. I use this. Yeah. And second member is E because it's only once. I need exactly 1, 1 per row. And then bound constraints, of course, I can take each schedule only once and not several times. This could be modified, but in our case, we will study this. Worst case, I just put twice the same column in the matrix if I want to take it twice. It's always possible. And of course, integrality constraints. That's the tricky part. So if you said you're all familiar with this, we can go faster on this. So this is typically the geometrical interpretation of this. I spend time on geometrical interpretation, so I like these kind of representations. So the red one is the linear relaxation, and the blue polytope is the convex hull of the integer points. We try to minimize, and we see that, of course, the integer solution may be quite far from the linear one, in terms of cost, of course, and in terms of solution itself. So to solve integer programs, most common method is branch and bound process. In our case, we try to look at on the other way with what is called primal algorithms. The idea is super simple. You start from an integer solution. If it's the best one, it's finished. If you can find a better one, you just go to the better one. So it's really the same as what the simplex does or what gradient descent is in continuous problems. And to solve this problem with primal algorithms, we solve what is called the augmentation problem. Augmentation is I stand at somewhere, and is there some better solution? I'll always make the difference between fractional and integer. So fractional augmentation, just find a better solution in the linear relaxation. This problem is, when I say easy, it's not easy. When the problem gets big, it takes time, but it's easier in the sense that it's polynomially solvable. And in practice, for example, the simplex algorithms, most of the time is quite fast. Of course, in the integer version, it's exactly the same that we want to solve, but the next solution has to be integer. Integer programming is a hard problem. Linear programming is simple in the sense of the complexity. And of course, complexity has to be reflected in here. So this one is easier, way more easier than this one. And the problem is to ensure that it's integer. So graphically, primal algorithms, I start somewhere and I go to the next one. If the green points are integer, for example, and the red ones are fractional, I'll try to go from one integer to the next one until I reach the best one. That's the idea. Just find a path of solutions and go to the best one. So before going further, why should we use primal algorithms? They are usually fast to improve a solution that you have. It can be just a few geometrically, solutions may be close. In terms of simplex pivots, they may be close if you have a nice structure of the problem. So if everything goes well, it can be very fast to improve a solution that you have. And it also prevents branching, in the sense that if you can find the direction that leads to a better solution, you don't need to branch anymore. Of course, finding this direction may imply branching, but that's what we try to prevent. And in practice, this is quite important also. Initial solutions that are close in the term of the geometry of the problem exist that are quite close to the optimal ones. And I'll talk about how they look like later or what they could be. Yeah, in practice, it's exactly this. So suppose that each driver is in a bus at the beginning of the day and just stays in this bus, on the bus route. This is quite close to the optimal solution because usually drivers don't change bus. Usually pilots don't change airplane. They often just stay in the same airplane if they go one and back. So these solutions in a primal sense, in the geometrical sense of the schedules that they use, are not too far in terms of routes that you have to generate. So this is quite an advantage. Of course, it's theoretically not faster because integer programming is complicated, so we can't just come up with a polynomial algorithm. And yeah, optimality proof may be harder than in branch and bound. It's because it may be even harder to prove that you are the optimal solution. And of course, column generation is always complicated to put in an algorithm, but it seems to be potentially more complicated here than in branch and bound. In branch and bound, you have the linear relaxation solution, which gives you dual variables and reduced costs, which you don't necessarily have here because you're always on the integer solution and not on the optimal solution of the linear relaxation. Primal algorithms works in the literature are either or mostly from the 60s, that's the theoretical part, and from the 90s and further, with the regain of interest. Yeah, namely Robert Weismantel and people who worked with him or next after him with literature and more modern literature. And the one that we base our work on, which is also from guys in the lab in Montreal, is integral simplex using decomposition. The principle is that you solve the fractional augmentation, so you find a better solution which is potentially fractional, and you hope in a way that it's integer. Of course, hoping is way more complicated than just hope. Decomposition is used, variable fixing is used, neighborhoods are used in the algorithm, but you add tricks. And it provides often an integer solution, but not often enough to be used in practice. So maybe 90% of the case you get an improvement, but if the path from the first solution to the optimal one is 30 steps, you have a good probability that it stops in the middle, saying I don't have an integer solution anymore, so I can't do better. And you can be quite far from the solution in this case. What we do here, or what I will present, are techniques of how to hope better, or how to make it more probable that we have an integer solution. So how can we improve the rate or increase the rate of integer solutions in this algorithm? And I'll present two or three different techniques. The first one is with cutting planes. So in branch and bound, you use cutting planes. And here in Primal algorithms, you can use cutting planes. We'll see how different it is and how similar it is. It's easier in a way, harder in another one, and I'll explain this. And then we will use normalization techniques or scaling techniques, either on a static basis, so you scale the problem from the beginning and then it helps, or you dynamically scale it up. So I'll present the main framework for the algorithm and then the improving techniques. So in the linear case, I start with the linear case. Suppose that we don't have the integral D constraint anymore. We stand here and we try to go as far as we can in that direction. What we usually do, or what we do in our case, is model the polytope that we have and just leave it as a cone. And this cone, any direction in this cone, is a direction I can take a small step in and still remain feasible. Usually you don't like to optimize on a cone because it's infinite. So we take a section of the cone, and that's how we normalize the problem, we scale the problem. So we'll see that this is quite important too. And among these red domain, among the section of the cone, we try to find the better vector. That the inner product with our optimization direction is the best for this one. It's better than for these or these. So we just keep it. We keep this one, and we just push it to the end. It's a gradient descent with the scaling. So on the algebraic point of view, the set partitioning problem looks like this. We have a current solution that is the solution that we already know, this one. So this is 1, and the other are zeros in the values that they take. So this one has 1, 1 on each row in this part of the matrix. It's a possible schedule for completing all tasks. So we have the positive variables and the 0 variables. This is different than in the simplex algorithms, where you usually complete the basis and have a square basis. We only keep the positive ones. And we see what is positive and what is negative. What is 0 and what is positive. And in the end, the augmentation formulation, the problem of finding a direction that improves is this one. We try to minimize the cost such that AD equals 0 means that we remain in the feasible set. And the bounds is that each variable that had the one value has to decrease and the other ones can only increase. So the positive ones can only decrease, the null ones can only increase. And this is a cone because AD equals 0 is a AD equals 0 plus the bound constraints is a cone. So we normalize it with any normalization constraints that makes this problem bounded. The set of normalization constraints that keep this problem bounded is not, the idea is not to determine the whole set of possibilities, but we see that, for example, having these ones, the WP negative and the WZ positive is, for example, sufficient because of the bounds that we have. So it's not too complicated to come up with possibilities. And then the solution that we stand at is optimal if and only if this problem has only a non-negative solution. Because if there is a negative solution, it means that there is a direction I can take a small step with a negative cost. So if I go to this direction, if I go towards this, I'm improving my solution and I still remain feasible. So this is for the linear part. So for the integer part, we'll first look at the specificities of the problem because it makes it easier to work. Set partitioning is 0, 1. So we know that all the integer solutions are also extreme points of the linear relaxations because they are at the bounds, 0s and 1s. So this makes it easier as we will see. And the set partitioning has another property which is quite strong, is that from the edges of the linear integer domain, all of these are edges of the linear relaxation too. So the blue polytope, the inner polytope, has all the edges that are also edges of the linear relaxation. We don't have edges in the middle of the linear relaxation. And this makes it a good thing because if we look for directions in the linear relaxation, all the extreme ones contain the integer neighbors. So this is a big plus. And we will impose that the next solution is a neighbor of the previous one. And that's how we will look for it. And we know we can do it because of this. Because if there are neighbors in the integer hull, there are neighbors in the linear relaxation too. And so we try to look for that kind of path. And this is possible because of the structure of the problem. So basically we were there with what we can do with the linear relaxation, and potentially these next neighbors are either integer or fractional. And what we do is we try to solve the blue problem with only 2 dots. The integer neighbors are a discrete set of neighbors, and we only have some of the edges. What we know is the fractional augmentation problem is a linear relaxation of the integer augmentation problem. So we can solve it as any relaxation and hope that we can find something good. And if we have troubles with this, we can maybe use cutting planes, we can maybe do something. So basically from the mathematical point of, or algebraical point of view, we just add this constraint. Okay, this looks super, these bound constraints are not the right ones. They are the same as before. I'm sorry for this. This is a super silly constraint because it's not, I'm not saying it, I'm not writing it in a mathematical form. But we impose to the next point that it's integer. And basically what we do is solve the relaxation and then we will see. So this is the pattern of the algorithm. Solve the fractional augmentation. If the next one, and go to the x star, which is the next solution. If it's integer, okay, I'll just take it. If it's not, that's what we will see. We solve the augmentation problem that is a linear problem and that we can formulate easily. That was the formulation before. And so I'll present this and then seeing what I can do. So first is the cutting planes, and then I'll present things that I can do either beforehand, or when I have troubles with the scaling that we can use. Are there questions up to now? Okay. So first, how can I do with cutting planes? Cutting planes in the branch and bound is just, I have a solution and I'll cut it off from the polytop. So what happens in here if I start there and I have three neighbors? Let's say the lower one and the upper one are integer, and the one in the middle here in front is fractional. Of course, let's say that the direction I have leads to the fractional solution, and that we have a problem. What can we do? So usual theory on cutting planes would say, let's just cut the fractional point there. So let's put a blue cutting plane here that just gets this one off the polytop and see what happens. So we have three new vertices, one here, one there, and one there. From a local point of view, my scaling is still the same. The possibilities, my cone is still the same because I just project it further. And so my domain here is still the same. And I don't do anything on my augmentation problem. And the only thing is that the step that I can take will only lead me there instead of the next one further, but I can still do it. The algorithm is step blind. It doesn't know how far I can go. It only knows the direction and the step. And okay, I don't have the word. It's gonna be hard. And the inner product between a scaled direction and this one. It's only, okay. It only knows how steep it is, but not how far you can go. So basically I can't do this. So I have to take off the whole direction from here to the next one. Otherwise I can still do a small step in that direction. So we need a cut that looks like this. That's tight at the current solution, and that cuts off the next one. And so this is called a primal cutting plane. Primal cutting planes are the same as dual ones, but they have to be tight at somewhere that you choose. In our case, the current solution. So we need primal cutting planes and not standard or dual cutting planes, they are called. And so in this case, I have a real modification of the domain of my relaxation here. And so cutting planes are a way of tightening the relaxation that I had. Exactly like in the standard algorithms or in branch and bound, but the thing I have to tighten is this one, so I have more constraints on my cutting planes. They have to be tight. And so, of course, if I'm close to a facet here, I will take off one more fractional point, and maybe the next solution is the integer one. But this is, in branch and bound, it's the same. If you can come up with the facets, of course, it's better than having to put, I don't know how many cutting planes before you end up to the integer solution. So they are tight at the current solution. They are theoretically and in practice faster to find than normal cutting planes. So it's more constrained. You have to be tight where you stand at the x0 or at the current solution, but this makes the separation algorithms easier and faster in practice because you work on less variables, because you have strong constraints on the ones that have to be implied in the cut or not. Typically the ones that you stand at or the ones that were in the direction. And so it's way easier to find them because you can look on a small part of the problem. Typically click cuts and odd cycle cuts, which are typical cuts for set partitioning problems, have a really good way of adapting to these kind of primal cases. And you make it very efficiently solvable. For the odd cycle cuts, it's polynomial to find to solve the separation problem. For the click, finding a click is not polynomial, but the number of variables on which you work is usually of the size of 10 to 50 maximum. And it cannot be more than the number of rows of the matrix, which is very different from finding a cut that implies I don't know how many variables in all this. And one other advantage is that they are valid only locally, because as long as you go off the point you stand at, they are not tight. They may not be tight anymore. And if they are not tight anymore, they are worthless for this algorithm. So it's a way of removing cuts, and you implicitly know which ones you can remove very easily. Of course, when you add cutting planes, you create fractional directions in the same way that in branch and bound or in cutting planes algorithms, you create other fractional solutions when you add the cutting planes. And of course, you add rows to the matrix, and you don't want more, I don't know, more cuts than constraints or too many more cuts. In the experimentations, I talk a bit about the instances before showing the results. We have aircrew scheduling and bus driver scheduling instances. So in practice, a pilot in the instances we have in the solutions follows the route of the aircraft roughly 75% of the time. This is typical for mid-range aircraft or mid-range planes. And in the bus driving problems, it's roughly 90% of the time. So we didn't have the aircraft routes because the company didn't give them, and we didn't have the bus routes either. So we generated solutions from the optimal solution. We knew the optimal solutions of these problems beforehand, and we generated solutions from these by swapping parts of the schedules until it reflects roughly 75% of the time the same, or 90% of the time the same for the different instances. And this 75% or 90%, we had 10 easy ones that are close to this or a little higher, 10 moderate and 10 hard one for each instance, where we perturbate it until it's not 75, but more like 65 or 70%, and not 90, but more 80, 85%, which is harder than in practice. And from the instances, so all these are aircrew schedulings. These are from the literature. These are from company problems that we have. And these are the bus driving scheduling. You can find them also in the literature. They originate from company problems. So typically on the small instances, okay, for this one, I only have experiments for the first two and the last ones. So for small problems, adding cutting planes make it go from roughly 50% of the problems solved. When I say solved, if you end up within 2% of the solution, you can consider it that that the company won't ask for more. So I'm considering this as solved.
The gap, you get it from yourself with the LP relaxation?
We have the LP relaxation.
So you
can use that as a lower bound, and it's usually we end up within 2% roughly the same number of times. We use the optimal solution. Yeah, the LP bound is tight, so it doesn't make much difference between this. Here we use the optimal integer solution that we know, because we know them beforehand. Yeah, and if you use the linear relaxation bound, you don't end up with very different results because the problems are quite tight in terms of bound. For these ones, it's a little less tight. For the other ones, it's really tight. It's less than 0.5, 0.3%. If you between the lower bound and the integer best solution.
It's not tight. You have no way of measuring progress.
No. No. At least not implemented. There are bounds on the how steep the direction is in the fractional term, and get how far you can go. Maybe add some cutting planes with this, but these are not very efficient. LP bound is more efficient. And so out-cycle cuts help worse than click cuts, but this is known for the set partitioning problems because there are less out-cycle cuts and they are usually further from facets. So this was expected. The only thing that we so of course, using both cuts is better. Okay, so okay, sorry, I was mixed up. Here is no cut. Here is click cuts. Out-cycle cut only. Here click cuts only, and here are two ways of adding them both. Either you look for both all the time, or you first look for click cuts, and then if you don't find them, you look for out-cycle cuts because usually click cuts are better. Funnily, it's slightly more efficient to look first for click cuts and then for out-cycle cuts. Out-cycle cuts tend to add more fractional points, because they are further to face it. So in the end, you prefer looking for them only if you don't find something else. And looking for them from the beginning creates fractional directions that may make the algorithm work a little less good. Sorry?
You don't lift the
We don't lift them, no. We don't lift them. I implemented lift, but it takes too much time. Maybe I don't know if I implemented wrong or if we have, or if it's not worth it. Especially for the big problems, it's really time consuming. Here it's smaller, it's some thousands of variables, but the other ones are bigger. And so on the large instances, here it's more from 100 to 500 something thousand variables. We have no improvement with cutting planes, so they don't make the solution better. But on roughly half of the variables, because we use neighborhood techniques, you can prove the optimality most of the time. So you end up at the optimal solution, and we have a proof here that it's optimal, because adding the cuts make the augmentation problem have a zero solution, so there's no direction that improves anymore. Sorry, what's the time?
It's 12:10.
Okay. So another solution is to change the way we normalize the problem, the scaling that we do. This doesn't modify the structure of the augmentation problem in terms of constraints. So we will still have all the possibilities of these directions, but the idea is to scale them so that some appear better than other ones. So for example, if I go here with this scaling, considering that I'm trying to go in that direction, D1 looks better than D2. And I want to go down D1, and I will end up at the fractional solution there. If I cut it this way with other weights, then now D2 appears better than D1. And I end up, and I end up to the integer neighbor. And so that's what we try to do. This is more heuristic in a way, or more handmade. We have some proofs for some constraints, for some weights, but the way of choosing the weights is the best way that we ended up was thinking of the problem and say what is good for an integer solution and what is worse. So changing the weights of the constraints is better than perturbate the costs of the problem, because of course we could perturbate the costs and of the original problem. When you perturbate the cost, the problem is that you may end up with a direction that looks good with a negative cost, but in fact it has a positive cost. And you may end up not knowing whether you're optimal or not knowing or thinking that you're optimal and you're not. And when you only perturbate the normalization, a direction with a negative cost remains a negative one, and a one with a positive cost remains still has a positive cost. So this can't change. You just make it appear more positive or more negative, but you don't change the sign of the direction. You don't end up with a decreasing direction becoming an increasing one for the cost. So that was something that we preferred doing for this reason. We know that there exists some scaling weights that if you use them from the beginning without ever changing them, you end up with a sequence of integer solution that ends up in the best one. Of course, the proof of this theorem is absolutely not constructive. Otherwise, we would have solved the problem. You suppose that you have a path, and afterhand, you reconstruct a constraint that would have been the one that you could have used to get this path. So it's good and bad. Theoretically, it's nice. In practice, it doesn't help that much. And if we choose a uniform cost vector, so -1s for the positive ones, +1s for the 0 ones, because some are decreasing, some are increasing, we end up with one of the most efficient algorithms in the network case for the minimum cost maximum flow problem, which is minimum mean cycle, in which you have a flow in the beginning and you try to cancel cycles in the residual network. And so these cycles that you use are minimum mean weight, and that's exactly what we get, the minimum mean weight. And yeah, some weight vectors can try to penalize fractional directions. And in practice, it works quite well. So the formulation is this one, as we said. So cost is here, and these are the cone and section of the cone. Cone constraints, and this one is the section of the cone that we use. And in this case, the larger the weight on the variable, the less likely you are going to use it. Because if you use it a little bit, you really penalize the weight that it has. Weight has to be 1, so if W is 10 for one variable, I will never use that variable more than 0.1 and probably less because I need also others. So we've proposed 4 strategies. This is the minimum mean augmentation because we make a mean over P and Z. Normalizing with WD equals to 1 is absolutely equivalent to dividing the cost by WD. So I can get rid of that constraint here and just divide the cost by W scalar D, the inner product of W and D. Of course, this is not linear, so I prefer to have it as a constraint, but that's why it's a mean cost, because we divide by the weight of the variables that we use. In the other ones, so interestingly, we just set 0 to the variables that are positive. It technically may not make it a full, wait, no, this comes later. I don't say anything with this. So this is a mean also, but only over what is incoming. I'm trying to bring as less variables as I can because the more variables I will put, the more weight I can risk, or this is the ID. So this penalizes the number of variables I'm taking in. And the more variables I'm taking in, the more likely they are to have ones on the same rows, and the more likely it is to be fractional. Yeah, that's what I was. This remains bounded because when I have negative variables and positive variables, so if I have some change, if some have to decrease, others have to increase. I cannot only have a decrease of the solution, current solution, because it wouldn't be a solution of the scheduling problem. I know that given the few schedules I'm using, I have to get 1 for each because I only have 1 on each row. So if some are decreasing, some other are strictly positive and both ways. So I can have zeros on one side, it's fine. I can have zeros on this side. I can't have zeros on the, I mean, being only zeros on this one works also because if I have positive here, I have negative here. But the risk is if I have zeros on both sides. So this is fine. That's what I was saying. This is still it's fine. And I can have this. And then we tried 2 of them. The idea is that the more ones, the first one, the norm of the column is the number of ones I have. The idea is that if I have a schedule that covers, I don't know, 100 tasks, it is very likely that if I take it in, I will have to get quite a good number of schedules out, if they roughly are, I don't know, 20 tasks. And probably to compensate this, I'd bring even more in. And this will probably create fractionality, because making it integer is the less column I bring in, probably the better it is. So the idea is that these ones may have ones on the same row as many other ones. So I don't want them. And this is the incompatibility degree, something we came up with. It is how it measures how far a schedule is from the current schedule. Typically, if the current schedule is this one, so I have 3 schedules for completing the 5 tasks. I don't know. This one only has 2 tasks and gets into troubles with 2 of them. So it's probably worse bringing this in and having to get something out than bring in, of course, this one I know I can bring it in because it covers exactly the same task as others. So this would be incompatibility degree 0, and this would have more incompatibility because it doesn't respect the tasks that are already together. So this is a way of doing. It even works better when you know that these are chronologically ordered. You can even end up with that kind of thing. So if I have 3 tasks, I know that these are chronologically one after each other, and I don't really want this because it means that I'm on one plane, then I'll do something else, then I come back on the same. It's probably worse than this and whatever is down there. But this is respecting part of the same schedule and then going to something else. And this is less incompatible with the current schedule I have than this, which is I'm doing this, do something else, come back on that plane, which I don't really want. This is very handmade. It doesn't have much to do with theoretical results. But in practice, it works quite good because of what I was saying, that in the primal sense, usually pilots stay in the same planes. Usually, this is what happens. We had different results with the different constraints. So this is on small instances. The one that was used before, which is ones on the 0 variables and zeros on the positive ones, ended up to be the one performing the less good. And the green one is with the norm of the column, number of tasks. It's something we tried because it looked, why not? And it's easy to implement because it's very easy to compute the number of ones in the column. This one is the one which proves to be efficient for the minimum cycle algorithm. And that we transpose into these problems. So equally 1 on all of them and performs well. And incompatibility degrees work better because of the structure of the problem and because of the industrial application it originates from. And so given that we know how the problem usually works in the industrial application and that we have industrial problems, it also works better. Interestingly, none of them solved all the instances, but all the instances were solved at least by one of them, which is the red graph. So we know that with these, we could solve all the instances we had, but none of them is neither. Okay, some are better than others. I mean, 95% is significantly better than 85, 90, but it's not perfect. Yes?
The upper curve is you apply one algorithm with one of the strategies throughout, and then you, or you mix up every
No, I don't mix yet.
Okay.
I just one constraint that I keep from the beginning to the end, and it's like at least one of these constraints work. No, this is all beforehand. Results on the larger instances are more. There's less difference. So this in the first column is the number of instances that were solved to optimality. Optimality meaning the integer solution that we know. This is gap between 0 and 2%, which we don't have too much because usually when it goes to there, it goes to the end. Gaps bigger than 2% also involves, usually they involved columns that were in the initial solution, and these in the initial solutions are the one we generate. And we give them a really high cost because they are technically, we don't know if they're feasible or not. As in the same way as following an aircraft may not be feasible for the pilot because of, I don't know, collective agreements, because the pilot can't fly the airplane 10 hours in a row, or I don't know. So these usually indicate that some infeasible columns still are in the problem. Okay, this is the parameter we perturbate with, which correspond to hard instances, medium instances, and easy instances. Usually, the typical complexity of industrial problems stand here. So we tried with little easier, little harder, somewhat harder. we get to solve from 8 or 10 problems out of 8 or out of 10. Each of them is 10 problems, and with the different constraints. And the only difference we can see in terms of number of problems solved is here and here. But so if you use the norm vector, which was already one of the bad ones before, you get more troubles here, but it's only one instance, so I don't think it's you can prove anything with this. What is interesting though is the computing time, which is roughly the same so for the 3 ones, and not the same for the norm constraint. Of course, the computing time does not include these instances, the mean time, because these stop prematurely. So it would be easy, it would be fake to say, okay, this one stopped after 3 iterations. I'm not counting this. It's only for those that go to the end or near the end. And interestingly, it takes less time to go to the best solution, less time to finish. And the number of augmentations here, it's usually, it's always in the smallest. So it usually takes less step to go from the initial to the end with this mean constraint, because it will try to go from the reason why it's efficient in the graph is that usually it goes, one iteration makes it go quite far in terms of improvement. And so improvements are usually better, each improvement, but it's harder to find these improvements. And when it terminates, it's faster. Same for the large instances, it's even more. So it's 20% to more, less time, 25% less time. It's faster, but it performs worse. Same here. Every time there is a problem, it occurs with this one. Okay, no. What did I say? I said something wrong. I'm not speaking about the mean augmentation. I'm speaking about the norm, number of ones on each column. They usually perform larger steps, but harder to find. And then what we can do is what you were saying, dynamically update them. So if it doesn't work, I'll use something else. So this is the easy way of doing it. If it works, it works. If it doesn't work, I'll just change the scaling. And for doing the update, I have information available. I know the optimal fractional direction, so the best direction in terms of fractional. I know it's fractional because I'm in this case. So the next solution is fractional, but I know this solution, this neighbor. I know potentially other that were found in other loops before. And I know also maybe cutting planes if I generated cutting planes or these kind of things. So we tried 4 strategies. The 2 first ones are super easy ones. Just randomly update the weights, add a random variable to each of them, and see what happens. Just random try. This one is try the previous ones in turn, starting with the one which statistically performed the best. And these 2 ones is the first one is the idea to penalize the direction that I find and the variables that are implied in this direction. And this one is trying to compute a penalty using cutting planes that we can generate. And I'll show how we can do this. So the first 2 one I won't explain more than this. It's just either random or alternate between these. So penalize the direction. The direction usually doesn't imply all the variables. It implies, we solve the problem with the simplex algorithm, so it implies at most the number of rows and usually way less variables. And we just penalize each of these variables such that if the variable is in the support of the direction, we just add some weight. And the others, we don't add weight. It's super easy, but it's an easy way of doing it, but it still penalizes the direction. The issue is which value should epsilon take? And of course, there is a risk of cycling. If I penalize this one, I go to this one, and then I penalize this, I come back to this one. In practice, we never observed cycling, but of course, there is no guarantee. Okay. And on epsilon, what we did is success and failure improvement. So if it's a success, we keep the same. If it's successful every time, we try to reduce it because it's maybe too powerful, or keep the same. And if it finds an integer direction, I'm trying to reduce it because I don't want it to be too high. If it changes from fractional to another fractional, I'll keep the same. It works. It's maybe not the best, but it works for changing. And if it isn't enough for changing, then I'll increase it by some number between 1 and 2. That's how we did. And using the cutting planes, I'll explain the geometry of the problem. It's easier to grasp than the algebraic one. I mean, I prefer showing pictures. So suppose we stand here. This is not 3D, but imagine these are neighbors. And we stand here, and as far as it is, the direction points to this fractional solution. Suppose I know a cutting plane to suppress that direction. I know the formulation of the cutting planes because since they are tight here, it has to be x minus x0. I mean, second B member can be put on that side. So I know this, and I know the vector alpha, which is a normal. Okay, and suppose that if I add it, I end up here, and it's fractional. I know the normal vector to this constraint, which is W, and I know the normal vector to the other one, which is alpha. And what I do is that I will add some proportion of alpha to W. In the algebraic, if you write the equations, you can prove that adding this will penalize everything that is cut by alpha and give some advantage to everything that is here. Of course, the problem is that the further you are, the bigger advantage you have. This is the only thing. I would prefer to get some advantage to the close ones because probably in terms of costs, it would be better. But I give advantage to these and I give penalty to these. And this is more, I'm not just penalizing some variables, but I'm really penalizing the geometry and the directions of this problem. And I know that everything which is cut is not an integer solution because I only have cuts that respect the geometry of the full problem. So I know that I'm penalizing fractional directions only. And so when I keep this one only, I don't know, maybe I end up to another one. Maybe I end up this, as I said, it's 3D. Of course, I end up with a vertex, but this is a put it up inside. So this is the idea. And I can do it with several cutting planes, making a mean of them and adding some weight for alpha. Of course, I don't want the shift to be too big, so I have the same kind of epsilon that I had before. I'm not adding alpha, but epsilon alpha. And if I can reduce epsilon, I do it. If it doesn't work, I'll increase it. The results we had, this is only some of the instances. So these are 2 instances from the aircrew schedulings we have that tend to be the hard instances. And this is over all the instances we have. So each instance is divided into 30, 10 easy, 10 moderate, 10 hard. So easy ones are here, moderate ones, and hard ones. Every time I'm solving 10 instances, and I'm looking at the gap if it's lower than 1% or 2% or bigger than 2%, which is something that we don't want. Usually 2% is a good measurement, or is something which is okay or not good. And so what we can see is doing nothing is definitely worse than doing something, because in every case, and especially in the easy and moderate one, it makes a big difference. So we go from 14 to 2 unsolved instances, or 23 to 9. And then from these ones, the global trend is that hyperplanes tend to work better. And they tend to perform quite fast too. They are usually among the fastest ones. So this was something that we were happy with. When I say hyperplanes, I compute the hyperplane, but I don't put it in the constraints because I don't want to add the constraints. And I'm adding the hyperplane is not necessarily it's not always necessary to change the solution that I find. Just shifting the normalization may be sufficient. And I don't want to add, I don't know how many constraints to my problem, so that I prefer to have more rounds with these and maybe solve it more times than solving less time a more complicated problem with the hyperplanes. And and what was surprising is that random is random in the end. So sometimes it performs super bad, and sometimes it's the most efficient one. It usually tends to perform slower because you need more iteration at each time before you find a nice random that works. But it was, I mean, sometimes it works, sometimes it doesn't. But this is, I guess, the thing with random. What was good is that in the end, we end up performing slightly or significantly better than random perturbation. But it's, I mean, it's still worth it, or it's still better than some other methods that we used. Okay, so basically, okay, I'll talk about future work that could be done with it. And the main thing is to embed column generation, because I presented solving static problems, but of course, if you want to solve scheduling problems, you have to add the column generation part. And the idea is to solve with it, with Primal algorithm, go to the next integer solution, generate new columns, and go from this solution to the best ones, to the better one. Yeah, so that's what I was saying. It's unrealistic to solve the instances, the real instances, in a static way, because then you need column generation. I mean, solving them in a static way, like generating, I don't know how many columns, solving the problems, you end up with let's say if you end up with a 5% gap with this, which could be typical, you end up with a 1 or 2% gap with column generation. And what we think is that the performances and the way the algorithm performs would make it better with column generation than it is without. In the sense that if you compare it to branch and bound as it is, I don't know how better or how worse it is. On small instances, simplex definitely beats the algorithm. On big instances, we run the computer 1 hour without finding a single solution with simplex. And when we solve these in the middle one in 90 seconds and the large one in 20 minutes. But if you feed with some other instance, I mean, we have some instances we solved them over. I couldn't make extrapolate for everything. But what is sure is that I think that the advantage it gets is bigger within column generation, because typically when you generate column, you want to go to the next solution, which may not be that far. And it's typically what we are doing. Take a few steps and improve a little bit, rather than go from the fractional solution again, branch something, which make it infeasible, which may keep feasible, and solve I don't know how many problems like this. And in the branching tree, when you have to go from when you were exploring one side and you go to the other one, this takes time because you have to resolve it, get the solution again, get the dual variables again, and you don't have the resolve, which is, I mean, it gets slower and slower every time you change branch of your tree. And so I think in this sense, it's better. And also what we observed but this is the way the instances are made. Some of them are from column generation. So we just do column generation with branch and bound. We keep all the columns that we found at some point, and we solve the problem, and that makes a problem, static one. And so we use these problems as our test bench for some of them. And the path of column generation is that you focus more and more on one part. So you have everything roughly kept with the initial variables, and you go somewhere and you usually detail this part. You add columns that go with this part. This is more hand or feeling of how it works. And so you tend to detail one side. And when we went on a path that went the other way, that's when we got in troubles, and that the algorithm stopped. Because column generation creates integer solutions, or creates a a higher density of solutions near some of the vertices that you use in the beginning of the generation. I mean, you go down some branches, but you don't go down every branch. And so in some places, you have a higher density of vertices, and hence of integer vertices, you have a higher number and higher, more connections. And as long as you remain in this thing, it usually goes to the end. And if you start going on, at some point, not the path the column generation that we used went, and if you go somewhere else, you stop. But what I think is that if the algorithm goes this way, if you do column generation, it's not a problem. You don't focus here, you will focus here. And if you focus here, you will go to the end. I don't know how clear this is or how easily understandable in my words it is, but this is the intuition we have. Yeah, so basically, given the integral simplex, we had the cutting planes. We have a proof of existence. We have some theoretical results on them, algorithms and computational results that I showed. And on the normalization, we generalized it used the difference with the previous version of the algorithm is that now we can scale as we want, what wasn't done before, even though it's just write one equation differently, but that's what has to be done with some proof over some constraints that are efficient, not efficient, or that exists. As I said, there exists one that leads to the best solution. I don't know how to compute it, but it exists. And yeah, the dynamic update proved to be way more efficient, of course, than static version of the algorithm. Thank you very much for your attention.